Hello, people, and welcome to this series of lectures, which is going to teach you how to do calculus, especially calculus 2 for all you college folks who are struggling through it. So, I'm going to provide some relief to you and give you all the tips and tricks which got me through to calculus 2 and help me secure a good grade. Also, I think it's important. I know it's a hard class. You have to work a lot, but don't worry. Hey, I'm here to help you out. Okay, we got this. We're gonna work on this together. So let's begin. Integration is essentially challenging. I mean, I get that part. It's no biggie, but there are some ways you can make it easier. Okay, so one of the ways which I think is important is systematically thinking about things. If you have a way like to systematically approach a problem, you're likely to make less mistakes. Okay, so my goal with this series of lectures is to give you a systematic approach in how to solving problems when it comes to integration, differentiation, or calculus. Okay, let's begin. In calculus 2, the first techniques you'll come across is there are actually many techniques in integration, but the first one you'll encounter is integration by parts. Okay, so let's begin. Before I talk about integration by parts, I just want to talk about like how this came about. Like why is this technique important, essentially, and like basically what's the origin of this technique. It basically has to do with the product rule of differentiation. Let me give you an example. Let's suppose we have a function. Okay, I want to differentiate this. To differentiate this, I have to use the product rule. So by product rule, I have to differentiate this first, keep this constant, then keep this constant and differentiate this, right? And add them. So let's do that. Okay, this will be e to the x, because the differential of this will only be 1, right? And now keeping this constant, differentiating this will just give me e to the x, because the differential of this term is just this. Making sense so far, friends? Okay, easy peasy, right? And we're done. So you notice that this term is essentially is in the differential. Weird, isn't it? All right, so let's try integration by parts. Let's say I want to integrate this. Okay, I want to integrate this to see if I get the original function back or not, right? Let me rewrite this in a better way so that all the math folks out there don't get angry at me. They must be looking at me like, what the hell? You're not writing proper notation, but honestly, I don't give a shit. But the problem is that just to appease them, you should probably write proper mathematical notation. So I bring d to the x here, and I integrate this. The integral of this will just be to the x, right? But the integral of this is not straightforward. For all those people who have not taken calculus 2, you know that this is not a straightforward integral. Why do I say that? So, okay, I'm sure most of you have done integration in calculus 1. You used u substitution, right? So you can do a u substitution here. Think of this as u du. This will break down to du. This will not work here. Okay, it would work if the function was this. Oh, sorry, if the integral was this, actually. If this were an x square, yeah, then it will work, right? Because the differential of x squared will give you 2x, and then you can manipulate it. But in this case, you can't, right? You're given an x, e to the x. You cannot just manipulate it to make it work for you. All right, so that's a dilemma, right? What do we do? How do we solve this dilemma? Easy. I'm going to teach you how. All right, so this is the integral we're stuck with, and we have to do integration by parts on this. For integration by parts, you essentially look at an integral and you make a choice. The choice is which one of these two will you differentiate, which one of these two will you integrate. Okay, what what dictates our choice? I mean, what is the driving force? Why do we have to pick one to differentiate? Why do we have to pick one to integrate? The goal is you have to make the choice of the one, you have to make the choice of differentiation first. Why do I say that? You want to pick amongst the two, um, the part which you can differentiate to bring it down to 0. Okay, so this, if I differentiate, I can bring it down to 0. This, if I differentiate, will always stay the same as e to the x. You cannot do anything about it, right? So just by looking at this integral, I know that I have to differentiate this, integrate this. All right. So the formula for integration by parts is u v minus integral of v du. So u is your choice of differential and dv is your choice of integral. In this case, the u has to be x and dv has to be e to the x. Okay, so what is du? I'm just doing du because I would need it for the breaking down this question further. So du is just 1 dx, right? And v is just what? E to the x. Okay, so now I have all the parts of this formula. I have u, I have du, I have dv, I also have v, right? Just plug and chug. Simple plugging and chugging from this point on. So x, v is e to the x. Okay, x e to the x, and then minus the integral of v is e to the x, du is just dx, right? Right. Solving this is easy now. It's x e to the x minus, this becomes what? This is just e to the x plus c. Since this is an indefinite integral, I have to add plus c to it. So folks, let's see, if I plug this back here, will I be able to go back to the original function or not? So we said that we had y is equal to, I'm plugging this down here, okay, bringing this down here for you guys to see. So y is equal to e to the x plus the integral of x e to the x dx, right? Now we know we have integrated this. This becomes x from here, e to the, from here actually, minus to the x plus c. So this and this cancels out. So this gives you y is equal to x e to the x. Woohoo! We succeeded. Okay, don't worry about the plus c part for now. So you see this? Great success in the words of Borat, which means that integration by parts is working. I mean, it works. It's a very powerful technique. Let's try one more question. Okay, let's try one with let's try one with I would say some trigonometric function. How about this? Let's try an integral with x cosine of x dx. Okay, does it make sense? So All right, so you know that in this case, it's simple, right? You know that u has to be x, dv has to be cosine of x, du has to be dx, right? And v has to be, so we have to integrate cosine of x, right? So cosine of x has to be, the integral of cosine of x has to be sine of x plus c. But we don't care about this for now, okay? So how do I know that? You know that if you differentiate this, let's say I differentiate sine of x, you get cosine of x, okay? So straightforward. All right, now let's plug in the formula. uv minus v du, right? U is what? X. V is what? Sine of x minus v is what? Sine of x. Du is what? It's just dx. Straightforward. From here, the answer should be x sine of x minus. Okay, now the integral of sine of x is a little bit different. You know that if you differentiate cosine, you get minus sine, right? So if you integrate sine, you should get what? Minus cosine, right? So this just becomes x sine of x plus cosine of x plus c. Okay, so when in doubt, do what? When in doubt, you can always try to differentiate it, right? So let's try differentiating it. All right, so let's try differentiating this, right? dy is equal to dy over dx is equal to what? We have to do it. You have to do it. Do the product rule here again, right? So this becomes. It's going to differentiate this, integrate. Differentiate and keep it constant. So sine of x plus keep it constant. Differentiate that cosine of x, right? Plus. Just have to do what with this? Just have to differentiate this. So cosine is minus sine is, right? So this and this falls off. X cosine of x, right? So have I convinced you guys? Dy over dx. So the differential of this gives us this. If I integrate this, I get this. Oh, sorry, not that, my bad. If you integrate that, you get this, right? So it all adds up. It makes sense, right? What if I tell you guys I can make your life a lot easier? I can make your life really, really simple. There is a method called the tabular method, which can let you do these things much faster. Okay, allow me to give you an example. Let's do this to the tabular method again. Do this with the tabular method. Okay. So this is an indefinite integral. For the tabular method, you draw a small table like this. On the left-hand side, you put your choice of differential on the left-hand side. On the right-hand side, you put in the choice of integral. Okay, now differentiate this. This becomes 1, this becomes e to the x. You differentiate down here, you integrate down here. Okay, do it again. Another round will bring you to 0. Another round will bring you to e to the x. So once we've gotten down to this 0, and we have the corresponding integral, draw arrows. Okay, the first arrow, put a sign of plus, second arrow negative. So you alternate the signs of positive and negative on these arrows. Okay, just multiply and keep the sign as a coefficient. So x e to the x. This is only e to the x, but the negative coefficient. That's it. That's your answer. So notice that this is the same answer as we got earlier, um, from uh, from integrating this by parts. So tabular method is a very efficient method when it comes to doing integration by parts. So imagine you have a very difficult integral you have to solve. Um, so hold on, let me give you an example of how powerful this technique is. Imagine you have this integral to solve. X to the fourth e to the let's say negative x dx. Okay, so this one is quite challenging, isn't it? You'll have to do multiple rounds of integration by parts to bring it down to zero. But look at this, how powerful this technique is. So I know that this one is the one I have to differentiate, right? So I'm just going to write it here, x to the fourth. And this one I have to integrate, right? So I'm just going to write it here. So first round of integration, first round of differentiation integration. So this is 4x cubed, right? And this is minus e to the minus x. Because you know that when you integrate this, it becomes e to the minus x divided by the differential of this, which is just minus 1, right? So that minus sign is just a coefficient now. Let's do another round of this, okay? So 12x squared, and now this becomes e to the negative x, positive, right? Another round, 24x, this becomes minus e to the minus x. Another round, this becomes 24, this becomes negative e to the minus x. Some people make the mistake of stopping here, since they think that, oh, we have gotten rid of the x, we stop here. No, keep going until you hit 0. So next round of integration differentiation will bring it to 0, and this will be e to the negative x. Arrows. So this is positive, negative, positive, negative, positive, right? So the answer is simple. Multiply. Keep in mind, in this case, you have to be cognizant of this coefficient, the negative coefficient, as well as this negative sign which you have to multiply. So just be aware of that. So minus x to the fourth e to the minus x, right? The second one will also be negative 4x cubed e to the minus x. Next one is again is negative. So negative 12x squared e to the minus x. Next one is positive. So 24x e to the minus x. Last one is also positive. So plus 24 e to the minus x. So that is your answer, guys. See how powerful this technique is. If I were to do this integration by parts over and over again, I would be stuck. I mean, this would become a very challenging integral to do. So yeah, that's about it, folks. That's an integration by parts, and in the next lecture I'll show you another problem which has to do with integration by parts, and essentially sometimes you cannot always bring this down to 0, so you have to do something else. We'll talk about it next week, or the next lecture. Okay, all right, thank you. Please leave some comments you have about this video. What do I need to improve on? Pardon my handwriting. Okay, that's the crux of becoming a doctor. Your handwriting goes downhill. But I will be happy to answer any questions you have, anything particular you want me to work on. Yeah, but again, this is a journey we're going to improvise together, and I would really love your feedback. Thank you.